Welcome to day 21 of the 2024 Advent of Code. For today's problem, not quite a grid problem I suppose, we have a numeric keypad arranged like so with the numbers going increasing order up, 0 in the center at the bottom and A in the bottom right corner. Unfortunately, this area is depressurized, so we can't go near this door, we need to send a robot instead. The robot will have its arm start at the A coordinate, and we will control this robot using a directional keypad. The directional keypad will be used to manipulate the robot's arm. So for example, if we want to type 0 to 9A, one way we could do this is by pressing left and then A to move the arm from A to 0 and then click it, up then A to move it to 2 then click it, right up A to move it up to the 9 and click it, and then down A to move it back down to the A and click that. So that's one possibility, and there are 3 possible sequences that are the shortest possible. All of those variants come from going from the 2 to the 9. We have 3 paths: up, right, up, and right, up. Unfortunately, there's high level of radiations in the area that the directional keypad control for this robot is, so we need to send a second robot in to press the first robot's keypad. The second robot also uses a directional keypad, and its arm starts at the A on the first robot and controls it. So for example, one sequence is to go down, left, A. Essentially what this means is this second robot's arm starts here and goes down, left, A, which pushes the first robot's left arrow, which moves its arm from this A to this 0. And so this is a possible sequence. All of these will send signals to the second robot, which will type something like this. I don't know which one of these 3 this represents, and that will get the first robot to type 029A. Unfortunately, the second robot has Unfortunately, the second robot's remote control is currently negative 40 degrees. Fun Easter egg, you don't need to specify Celsius or Fahrenheit for negative 40. And so unfortunately we need to send a sequence to a third robot that will then command a second robot to command the first robot to type in the original sequence. So in total we have the keypad that we use, which we input into the last robot because it is full of historians and no robots can find a clear path, so we'll have to do it ourselves. One keypad that is directional that we use on the farthest robot in this stack, then 2 directional keypads used by the intermediate robots, and 1 numeric keypad on the door that the last robot in this sequence is using. If a robot arm is ever aimed at a gap where there is no button, the robot will panic. So basically we're not allowed to go onto the gap that exists. In the numeric keypad, that means we can't go in the bottom left corner. In the directional keypad, that means we can't go in the top left corner. So without the insight of what part 2 does, I will show you how I originally coded this. It is not the most efficient, but in the interest of showing you how I originally did this, I will show you that. And also that way we can work through part 2 together and it isn't just a case of just change a number or something like that. So for each of these, we have some number of shortest possible sequences. There may be more than one that have the same outcome. And we want to figure out the complexity of each code. A code's complexity is the length of the shortest sequence of button presses needed, doesn't matter which one, and the numeric part of the code. So for 029A, that's 29. And then we take the product of those 2 and add up the complexity of each of the codes to get our answer. So we're going to make a general solve function, and what the solve function is going to do is it's going to receive a string that we're attempting to type, the grid, and the initial position. Actually, no, we don't need the initial position because it's always A. So let's make a solve function that takes a line that we are trying to, a string that we're trying to type, a grid which represents the keypad, and returns the list of all shortest sequences that would work. So for example, in order to get the first robot's output, in other words, the one controlling the keypad directly, we are, the reason I'm doing this is to strip the line of the ending new line. And the way we'll do this is, let's print out the line and we'll print out solve line keypad. We'll get rid of all of these for now and just look at this example. So the keypad here is going to be this grid. And so we'll call this one the door keypad, which is 7, 8, 9, 4, 5, 6, 1, 2, 3, and we'll give this a value of none to indicate that we cannot hover over it. That will be our first keypad, and the directional keypad, or the robot keypad, let's call this num keypad, will be blank, up, A, left, right, or sorry, left, down, right. So we'll solve the first line using the numeric keypad, which is this. And so in order to solve, we're going to need to basically perform a search across all possible inputs to get us from point A to point B, and then press A to push it down. So this will always output a sequence of up, down, left, right, and A, which basically tells each subsequent robot in the stack what inputs it should do in order to manipulate the previous robot. So for example, 0 to 9, A with the numeric keypad input into the solve function should give us the list of these three outputs. And then one of these input into solve with the directional keypad should give us a list containing many sequences, one of which will be this. So we're going to first get the position of each key. And so the way we're going to do this is for R in range length keypad, for C in range length of that row. Basically, we're going through each coordinate. The position of the character at that point is going to equal the coordinate pair RC. And note that we only want to store this if keypad RC is not equal to none, because we don't care where the blanks are and there might be multiple, and so tracking them doesn't really make any sense. And now we're going to pre-compute the possible sequences between each two, because we don't want to have to repeat that over and over again. And so the way we're going to do this is we're just going to create a map from each pair of potential input values on the keypad to all sequences that can get us between those 2 points. So we can call that sequences, and then we can do the following. For X in pause and for Y in pause, if X is equal to Y, then the only shortest sequence to get us from a point to itself is to obviously not move. And so the sequences for that is just going to be, the only outcome is to just press A directly to just push the button again. Basically, this is telling us if we are currently at X and we want to press Y, what is the list of all optimal ways of doing this? And if X and Y are the same, we just push A to confirm again and skip past this option. Now, if they're not the same, we're going to do a breadth first search. By now, you should hopefully be fairly familiar with these if you've been following on with the rest of the videos. But basically what we're doing here is, if, for example, we're trying to get from 2 to 9, it doesn't matter what these numbers are, we're going to first look at this one and add it to the queue, which represents the list of all positions that we know we can reach but have not yet looked at. And then we will look at its neighbors and add them to the queue. And then we'll go through that queue and look at its neighbors. And once we eventually find the end position, unlike in usual BFS, we're going to do two things differently. First of all, we're not going to stop when we find the value because we don't care about one shortest path, we care about all shortest paths. And second of all, we're also not going to keep track of duplicates. And the reason for this is because we're also going to keep track of the path we used to get there. And so there might be multiple paths to get here, and we want to look through all of those. Now, we could theoretically optimize this by adding the path to get to that into the previous entry. Basically, instead of adding 2 entries, we have each entry track all possible ways to get there. That would theoretically be slightly more optimal, but given that the maximum possible path length here is only like 6, it is really unimportant, and so we shouldn't bother wasting time doing that. In fact, it might not even be more efficient at how small of a scale we're working with our numeric keypad being this tiny. So we're going to keep track of the possible sequences to get there. So we'll call that our possibilities. And at the end, we'll assign the possibilities like so. And so our queue is initially going to contain the position of x paired with the sequence we've used to get there, which currently is an empty string representing we have not yet moved. And then so long as we also need to track the minimum length to get there, because there will be ways to get there that are suboptimal, like so. We don't want to track those. So once we start, because the BFS algorithm always looks at the closest values first, so look at distance 0, then distance 1, then distance 2, then distance 3. What that means is the length of this string as we iterate through each of the items in the queue will never go down. And so once we find a sequence that gets us to our target that is longer than optimal, it means all future sequences will be longer than optimal, and so we can stop looking then, but only after we've found the last possibility. So we're going to keep track of the optimal length, which is going to initially be infinity. Or we could even just do like 100, but infinity. And now, so long as the queue is not empty, we will keep looking through the queue. So each entry of the queue is currently structured like so. It is a position paired with the sequence we've used to get there. This is a string, and this is a pair containing the row and column coordinate of the position. And so the structure is going to be a pair containing the row and a pair containing the left side, which is another pair that contains the row and column, and the right side is the current sequence, or we can call it the moves that we've used to get there. And now we can look at our possible options, which are to move up, left, down, or right. So for NR, which is the neighbor row, NC, which is the neighboring column, and the next move, which is the move to get to the next position in our possibilities. So we can go up, we can go down, we can go left, and we can go right. We'll look at some possibilities. So first of all, we need to make sure that this position is within the grid. So that means that it needs to have its coordinates within the bounds of the grid, and also needs to not be over the none positions. So if NR or NC are out of range, then we skip it. If that position is none, then we skip it. And then we have two cases. Either this is the end position or it's not. So if keypad NR NC is equal to Y, meaning we have found the position that we're looking for, then what that means is we need to add this to the possibilities and then continue on without adding this to the queue, because we don't want to keep looking beyond the end position. However, if we've already found the optimal length, so if we found the optimal length and it is better than our current possibility, so the current sequence we have is moves plus nm, and so the length of that is length of moves plus 1, because nm is always length 1. So if optimal is shorter than the current path we have found, then we will exit the loop. In order to ensure that this exits this loop as well, we're going to again use the else continue break construction. I've used this a couple of times this year, and I also have a YouTube short explaining this in full. But essentially, break will skip past this continue and jump to this break. So this break will also cause the outer loop to exit. But if we don't break, then this for loop ends without finding an option or without quitting, and then goes to the else block and continues back to the top of the while loop, skipping over this break. So this basically propagates breaks outwards from a loop. It's not the most elegant solution. Typically, if you have nested loops and want to skip out of the inside, you should probably put it in a function and return. But here it's a bit difficult because we have a bunch of variables that we'd also need to pass through to the sub function. So let's continue doing it this way here. If otherwise, we can do optimal is equal to length moves plus 1, basically meaning we have now found the optimal length to get there. Even if optimal is already set, this is going to be equal to it, so this is just going to not do anything, and I'm not going to bother checking if it's equal before setting it. And then we also need to add it as a possibility. And the possible outcome is moves plus nm, plus the A to actually push the Y button. Otherwise, if we have not arrived at Y, then we just need to keep looking. So q.append nr nc moves plus nm. This continues the sequence, telling us that we can get from x to this coordinate position using these moves. Now, theoretically speaking, we could cull duplicates early by storing a map from each position to the optimal way to get there, so we don't add things that are suboptimal, but that seems like too much work considering that our time is going to be bounded by when we find all of these possibilities, which is a maximum of 1, 2, 3, 4, 5. And that number of iterations is just not worth culling duplicates for. Even if we go back and forth between two values, it doesn't matter. We're going to build up a bunch of excess values, but it's not going to influence the time overall too much. Now, I'm going to add this optimization in later because it actually turns out that the solution is a bit slow, but I have not done that yet because I didn't do that during the contest, and this doesn't work for part 2. So we'll find out together how much of an optimization this actually makes. So now we have all of our possibilities. So if we print out sequences, we should be able to get wrong brackets. We should be able to get our sequences. Okay, wait, what am I even storing in this? That's telling me it has length 2, and yet it's telling me 2 of any values. That's yeah, okay. It's because I appended it incorrectly here. Sorry. Structural issues aside, because I did make it a pair and a string. This basically tells us all of our sequences. So this might look a bit daunting, but let's look at some examples. So for example, to get from 9 to 6, we have one option, go down and press A. To get from 8 to 2, we have one option, go down twice and press A. To get from 8 to 3, that's where we get 3 options. We can go down, down, right, A. We can go down, right, down, A. Or we can go right, down, down, A. So this now gives us all of our options for each pair. And so now we just need to look through all of the possibilities. So basically for each pair of adjacent characters in the string, we will get a list of possible ways to get between them. And since each of these are optimal, then the list of all optimal solutions is going to be obtained by just getting every single possible combination. So essentially, for example, to get from 0 to 2, we have one possibility. To get from 2 to 9, we have 3 possibilities. To get from 9 to A, we have one possibility. This will give us a total of 3 possibilities. If we pick a bit more of an interesting example, such as 0, 3, 5A, there are 2 ways to get from 0 to 3, 2 ways to get from 3 to 5, 3 ways to get from 5 to A, which means that we will have a total of 12 options. And so these are the possibilities. Upright. Sorry, up. Is it upright? It is upright. Upright or right up. Up left or left up. And down down right down, or right down down. And so we want to get every single possible combination here. So like this, 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 etc. Basically, we want to get every single way of picking one of each of these. This is known as the Cartesian product. And the Cartesian product is probably easiest done by just importing it. We can import the product function from itertools, which stands for iteration tools. It comes with a couple of utilities. The one we want to use here is product, which takes a variable number of arguments and takes the Cartesian product of all of them. So we're going to get the sequence between each pair. So let's call that options is going to be the possibilities between each pair. And so for each pair, which you can do by taking the zip of two lists. So let me quickly explain this. If you zip a bunch of lists, you go through in column-wise order. So for example, if we zip the lists 0, 1, 2, and 3, 4, 5, 6, we would get the pairs 0, 3, 1, 4, and 2, 5. Once one of these lists runs out, everything else is ignored. So if you want to get the pairs, the adjacent pairs in a string, you can zip itself by itself offset by 1. And the reason that works is because this list will be 0, 1, 2, 3, 4. This list will have the first element removed. And so each pair will be with the element and the element that comes after it. And the last value is disregarded, meaning we get all of the adjacent pairs. And so that would be done by doing zip of string with itself. Except here we have another unique case. Because we need to account for the fact that we start our robot arm on the A key and not on the first key in the string, we actually do this. We put the A ahead. So now we have A 0, 1, 2, 3. And so we can't slice off the first value, otherwise we would actually be getting pairs that are separated by 1. So in this case, we would actually be doing this. And so for x, y in zip A plus string and string, x, y is each pair of neighboring characters in the string. And so we can get sequences x, y. If we print out our options like so, we can see that we have this. To get from 0 to 2, we go left and press A. To go from 2 to 9, we go up and press A. Sorry, this is to go from A to 0, from 0 to 2, from 2 to 9, and from 9 back to A. If I go back to the more interesting example of 035A, we get A to 0 is still the same. From 0 to 3, we have 2 options. From 3 to 5, we have 2 options. And from 5 to A, we have 3 options. And so then we can take the itertools.product of the options. Sorry, I just imported it as product. Except this doesn't quite work because itertools product doesn't allow us to give a list of lists. We have to provide it each list in a separate argument. So you have to use this. If you're not familiar with this in Python, I'd recommend learning about it. It's a very useful tool. Essentially, it takes a list and dumps all of its arguments into a list. So for example, running f of 1, 2, 3 with its arguments distributed using the splat operator, it's the same as doing this. And this gives us all of the possible ways of getting it. And we also want to merge these all into one string. So we can say empty string.join x for x in product of options, which gives us a list of strings, each of which are a shortest option. So you can see that there are 12 here. And if we go back to our example of 029A, you can see that as per the example problem statement, there are exactly 3 options here. And finally, we can just return this to get our solve function. So now that we have this, this is our first level. This tells us what the first robot needs to do. It needs to pick one of these options in order to type this desired string into the keypad. Now let's move on to the second robot. The second robot needs to manipulate the keys of the first robot, and so what it needs to do is find a way to move its arm around and such that it can input one of these options. And so we don't know which one of these will have the best possible outcome when we move it into the other robot, so we are going to try all of them. So what we are going to do here is make a list of possible robot 2, and then for each sequence in robot 1, we're going to solve it with the directional keypad instead, because we're trying to manipulate robot 1's keypad, which is directional. And we're going to add all of those to possible robot 2. So that gives us this, which is a long list. However, not necessarily all of these are optimal. And so we're going to get only the ones out of these that are optimal. And so we're going to get the length of the shortest one. So min length equals min of map len over possible robot 2. That tells us what the length of the shortest possible outcome is, and then we just filter it. So robot 2 is equal to each sequence in possible robot 2, only if the length of that sequence is equal to the minimum possible length. And so now we can see that we have filtered it down to just the optimal outcomes. And if we take a look at the example, this should be one of the possible sequences. We see that it indeed is, and we know that it is optimal, and so all of these are optimal because all of them have the same length. Finally, we need to do this one step further because we also need the robot to press the second robot's keypads, and so we can basically just repeat this step again. And so in order to avoid duplicating this code, what I did was just for blank in range 2, I just did possible next, and instead of robot 2 I called this something like next. And so we can see here that the length of the third sequence is right, I forgot that we can't keep using the robot 1 value. We need to update the next value each time. And so this will give us 68, which is the length of the shortest possible sequence for the third robot in the line. So now what we've basically done is we've made a general solve function that can take a keypad and a string that we're trying to type in, and starting from A, it will tell us what movements each robot should make to type on the next one. We start by taking the line, which is what we're actually trying to print or input. We solve it using the numeric keypad, which tells us what the first robot should do. And then we assign next, which will keep changing within this loop that runs twice. And for each time, we'll look at each of the possible sequences that the previous robot could do, and then add all of the ways that the current robot can input that sequence into the previous robot, and then filter only the ones that are optimal. And finally, that gets us our length. And again, remember that the complexity is determined by the length of the sequence times the integer value of what we input, which is going to be all but the A in the line. And then total is increased by complexity, where total is some value that we're going to use to track the total complexity. And that will give us our total, which if we copy the input back in, will give us our answer for part 1, although it is slightly slow. Now, I mentioned this earlier, but when I first solved this, I figured that because the grid was so small, any pre-computation didn't really matter too much. However, I am curious now if it would actually make a difference, given that you saw that part 1 did take several seconds to run. Now, granted, during the actual solve, given how long this problem takes to work out, a couple seconds isn't really going to matter that much. But I do want to know what happens if we pre-compute this in advance. And so I'm going to make a function that computes the sequences between each key on a keypad. And it's going to do this and just return the sequences overall. And so if we just drop this in as a placeholder, sequences equals compute sequences for keypad, it'll still work for part 1, but it'll be a bit slower. Or sorry, it'll be the same speed. And if we then pre-compute this, we can do num sequences equals compute sequences for num keypad, and directional sequences equals compute sequences for directional keypad. And now, because we don't actually need the keypad except to compute the list of sequences, we can just feed the sequences directly into the solve function, like so. Yeah, okay, so like I thought, it actually does not really make a difference. This giant loop, despite taking up most of the code's space, actually is not the bulk of its time loss. Which makes sense. The bulk of its time loss is from the fact that we're looking at a lot of options here. Sorry, that's not at all what I meant to print. We can see here that in our test input, we have about several tens of thousands of options to scour through. Here we can see that for one of our cases, we actually had 262,144 possible shortest sequences, which means that before we did our culling, we had even more, which means that we're looping through a lot of possible things to solve. So even if we cut out this step, we still just have way too many things to look at, and going through each of itertools.product and looking at all of the options is just too slow. So let's see what part 2 has to offer. Instead of 2 robots in the middle, we have 25 robots in the middle. So as you can imagine, given that we're getting exponential blow up on the number of possibilities, we can't just change this 2 to a 25. That, in fact, just changing it to a 3 already causes my computer to start lagging because of just how many possibilities there are going to be. So we need a much better way of solving this. And so this took me quite a bit of time to think about, but what we can realize is that the reason we have so much memory consumption is because we're doing this in breadth first order. Basically, we're looking at our code, we're getting all of the ways that we could type that optimally, and then we're looking at all of the ways to type that optimally, looking at all of these options together, and then looking at all of the ways to type any of these, etc. This means that we're tracking a lot of stuff at once, and our total memory consumption blows up exponentially. But what if we just instead picked one branch, went all the way to the bottom, looked at it, and then looked at the next branch, and then proceeded up a branch, etc. What if we did this instead in depth first traversal? That would mean we take up a lot less memory, and that would indeed work. Now granted, that would still take a lot of time because we need to go through all of these options. However, what we can do is we can note that we can memoize or cache a lot of this computation. Because one thing that you may have noticed is that we were able to isolate the calculation into each adjacent pair. The context of the full string actually does not matter at all. All we really need is to know, given two characters x and y, what is the best way to get from x to y for the nth robot? So for example, for the first robot at a depth of 1, getting from x to y is just this that we pre-computed. For the second robot, if we go from x to y in the first robot, and for example, we get a sequence of like upright up A, then next robot's optimal way to get from x to y with depth 2 is to just look at the optimal way to get from up to right, and then the optimal way to get from right to up, and then the optimal way to get from up to A. Also at the start, we need to go from A to up at depth 1. And it can compute all of these separately. So if we break down one of our earlier examples using this, just so that we're a bit more clear on what we're doing, we basically, to solve 0 to 9a, we're trying to figure out how to get 0 to 9a in depth 2. Or I guess it would be 3. Since the first step is a bit unique, let's just skip past it. Up A, up A. Sorry, that's meant to be left A, up A, right up A, down 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 A. So that's the first depth, which decreases our depth counter from 2 to 1. And now in order to figure out how to get between right and A in depth 1, or I guess first we need to go from A to left in, I can't speak today, from A to left in depth 1, we can just look at all of the possible sequences between A and left, which, looking at the second keypad, is down left left A or left down left A. So that gives us two possibilities: left down left A and down left left A. And then we can just look at each of these pairs at depth 0, which we've already pre-computed. And so we can basically do this recursively, and then when we get to this pair at depth 1, we will probably end up running into duplicates here, and because we've pre-computed them, we can skip over the computation. And now you can imagine at depth 25, going up even further, if we arrive at a branch that has some pair at depth 24 that we've already computed over here, we can skip an entire tree of computation. And so this should be fast enough. So instead of doing a loop, we're going to do this recursively. And so we're going to need a function that tells us the length of the shortest possible sequence between 2 points at a certain depth. So this will probably make a bit more sense when I start computing it. I know this explanation is a bit unclear, sorry. It's a bit hard to explain it because there's no good visualization for this. But if we make a function that computes the length from x to y given a depth initially of, let's do 2 so we can test it against our part 1 code, we're going to basically still keep the first step, which solves the line for to get from the number keypad to the first robot's inputs, and then compute length will just take the first robot's inputs one character pair at a time and compute the length for each of those, and then we just sum it up to get the answer. So we're going to also import a third utility here, the cache function from func_tools, which basically is a decorator that you add to a function to cache its values, basically preventing them from being recomputed. You can see this in action if I pull up a quick example. We can just return x. You can see that the first time I call f on 1, I get the printed output computing 1. But the second time I call it, at cache has made it remember the value, and so we do not compute it again. Like so. So if the depth is equal to 1, actually, sorry, I forgot that we don't actually compute at depth 0, because at depth 0, we're not actually moving between these keys. We're just, these are the arm movements directly, not the keys that it's trying to press. If the depth is equal to 1, then we already have the direction sequences. So it would just be the length of their sequences of x to y. And we can just pick the first one. Now, it doesn't make sense to do this step repeatedly, so we can also do dir lens, which is perhaps this would be a bit more suitable. It tells us the length of the shortest possible sequence between two keys on the directional keypad. We don't need this on the numeric keypad, but we do need this on the directional keypad, because we simply wouldn't use this on the numeric keypad. So this is going to be for each pair in the directional sequences, it's going to be the length of the first item in the list. So if we do directional sequences.items, that will give us a list of pairs of its key and value. And we can just go from key to the length of the first item in value. In this case, value is the list of all sequences that gets us from X to Y. So we can just pick the first one since they're all the same length and take its length. You can see here, for example, that it tells us that to get from up to up is length 1. Makes sense because we need to press the A button. To get from right to left is 3 because we go left twice and press A. To get from left to A is 4 because we go right, or right up, and then press A. Except this time we don't actually care about the sequence itself, we just need to know the length. So if the depth is 1, then that means that we're trying to get our robot to directly go from the X button to the Y button. So we don't want to recurse one step further because this is the robot that is manipulating that keypad. So we just need to return the length of the sequence on the directional keypad from X to Y, like so. Otherwise, we're going to need to recurse one level. And the way we're going to do this is we're going to look at all of the possible ways to get from X to Y, which will tell us what the robot before it needs to do, which reduces the depth by 1. And then for each of those, we just compute the optimal solution. So this is supposed to output a number. So we're going to get the optimal length again, which is initially infinity. And then we will say for sequence in directional sequences for X, Y. This reduces the depth by 1. This now gives us the sequences of the robot before the robot at this depth. And so then we'll get the length equals 0 here. And then for each X, Y in zip A plus sequence, this is the exact same construction as I did earlier, where we iterate through each pair of values that the next robot needs to go between. Length is going to plus equals compute length for X, Y at a depth of just 1 less. Sorry, I just realized that X, Y are bad names here. Let's call this AB. So you'll notice here that this is sort of doing a similar thing here, where basically we are going from a sequence to the next sequence by just repeating the solve step on it. But we'll note here that we have broken up the steps, the pairwise steps, and instead of returning the full sequence like we do from the solve function, which requires us to keep track of the entire sequence, we instead look at a pair in the sequence and then dissect it directly. And this, if the depth is still greater than 1, is going to look at the first pair in its possibility and recurse again. So we're recursing first and then coming back up with just the number, which prevents us from having to store a large string. Without the cache step, this would take the same amount of time, because instead of going row by row, we'd be basically going down branch by branch. But with the cache here, this allows us to skip large amounts of computations. So now we can say optimal equals min of optimal and length. And at the end, we can just return the optimal value. So now we have compute length. This is a function that takes 2 keys on the directional keypad and the number of robots remaining to compute, and tells us the best length for our top level robot, which is the shortest sequence that we can use to input this pair. So we're going to still keep this first solve step that solves for the numeric sequence, and we'll call this inputs. So we still have the same stuff here. So for example, for 029A, we still have 3 possibilities and we still need to check all of them. For 379A, we still have the same 6 possibilities as before, and we still need to check all of them. You can see, for example, that 208A is a bit more of a complex one that has a total of 9 possibilities. And so we're going to need to try each of these. So again, we're going to have an optimal length here. And for each possible sequence in our inputs, we're going to compute its length. In order to compute the length of a sequence directly, we're basically going to repeat this part. So for x, y in zip a plus sequence with sequence, length plus equals compute length between x and y, and then optimal equals min optimal length. And if we print out this optimal value, we can see that at least for the first one, it gave us the same length, but you'll notice this time that it is quite a bit faster because we are saving a lot of computations and not storing long strings. Storing numbers is a lot nicer than storing long strings just in terms of memory, and that does matter a lot for time as well. Now, I don't quite like how this is duplicated here. I do think that we can make it so that instead of compute length calculating a pair, we can make it calculate a sequence instead. So if the depth is equal to 1, then it's just directly the lengths between each pair. So we can just say return the sum of dir lengths xy for xy in zip a plus sequence. Otherwise, for each sequence, we look at this and then return. No, sorry, this will not make sense here. I guess rather for each pair in the sequence, we're going to look at the possible sequences between those. So that would be for sequence in direction sequences between x and y. We look at compute length of that subsequence at a depth of 1 lengths. Okay, so basically this is doing the same thing. Instead of having a pair and obtaining its subsequence and then looking at each of these pairs and recursing on those, we instead have a whole sequence. And then we look at each pair and evaluate its sequences and find the optimal one from there to bring up. So this is basically doing the same thing, because at the end of the day, we are taking a pair, expanding out into its possible sequences at 1 greater depth, and then breaking it down into its pairs. So this step and this step, we can either do them in the pair to sequence, then sequence to pairs order, which is what I did previously, or we can do the sequence to pairs step and then the pairs to sequences step, which is what I'm going to do now so that we can avoid some code duplication. Do note that when I did this during the contest, I did it the first way. This is just a bit of hindsight, I guess. So now we're going to look at the best possible subsequence between these. So that's going to be the minimum of compute length of the subsequence for each subsequence possible. And this is going to be the subsequence length. And so because we've done our optimization step outside, previously I did the summation on the inside and then the optimization on the outside. Now we've basically done the optimization on the inside, and we're going to do the summation on the outside. So this is going to be length equals 0, and then we're going to do length plus equals. So in case it's not entirely clear what I'm doing here, basically for each pair in the sequence, we know we have to execute the sequence, so we know we have to go through each pair. For each pair, we look at all of the possible ways we could get from x to y, and then we compute the length at depth of each of those sequences, get the best one, and add it to the length. And because we need to get through each pair in this sequence anyway, we can optimize each pair and then take the sum, and it's the same thing as taking the sum and then optimizing for the best length. So this also lets us skip over this, because now we don't have to do this iteration again here. We can just say that we've already gotten a function that'll take a sequence and a depth and compute the optimal length. So we can just directly have print compute length of inputs, or I guess sequence for sequence in inputs. This will tell us all of the possible lengths. So for example, what this is saying is that although initially, in order to enter 0 to 9a, we had 3 options that were all equal lengths. The first one, at depth, has an optimal input of 68 when we account for the fact that we need to input a sequence that commands a robot to input a sequence that will command this robot. The second one only has an optimality of 76, which makes sense because by alternating between the up and right keys, that causes us to have a bunch more intermediate inputs. And the last one is the exact same. And so now we just need to get the minimum of this, min of compute length sequence for sequence in inputs. Or I guess we could just do map compute lengths over the inputs. Compute length over the inputs. That will give us the best possible sequence at depth. And now we can just do the whole complexity calculation again. This is going to be the optimal length, and then total plus equals length times int line up to the last character again to get our optimized solution for part 1. And you can see just how much faster this runs. And this also leads perfectly into part 2 because we just replaced the 2 with a 25. And that gives us our answer for part 2, which you can clearly see we would not be able to calculate using the primitive method from the first part, no matter how many optimizations we try to do to that, simply because you just cannot store that many sequences. So this was a very fun challenge, and it does seem like in the spirit of Advent of Code as per usual, the weekend problems do get significantly harder. The difficulty spike from yesterday to today was pretty heavy, I'd say. But I had a lot of fun with this problem, and as an added benefit, it seems to have completely screwed over all the AI cheaters, because this problem is a bit too complex for LLMs currently to be able to figure out on their own. I'm sure the diagrams in the code also did not help. In any case, thank you very much for watching, and I'll see you again next time.